All right, so I'll start with any questions over homework, over anything. Number 10. On page, that one right there? The 12 and 7/9 plus 3 and 11/12, that one? Okay. So for number 10, we have 12 and 7/9 plus 3 and 11/12. Right? Okay. So we're adding these two, what we call mixed numbers together. And I said if we're going to do this, we should probably do what first?
Get rid of the 12.
Get rid of the what?
The 12 and the 3.
Okay, so turn them into improper fractions. All right, it's a bad name. Improper fractions sounds like you're doing something wrong, but you're converting it from this notation to a different notation. So I'm going to go 12 times 9 plus 7. So what is it? 115 over what? 9. And then over here plus 3 times 12.
47.
Then plus this is 47 over 12. Are we good up to this point? All right. Now at this point in time, you have to find a common denominator if you're going to add these two together. So you have to come up with a multiple of 9 and 12. And any multiple, but we always like to try and find the smallest one. Is this where you're having an issue, or yeah?
My answer is just the big.
Is real big? Okay. That could be the case. Here's a way, if I was actually going to go and look for the least common multiple, I would list out all the multiples of 9 and 12 side by side until I get to one that matches. So 9 times 1 is 9, 9 times 2 is 18, 9 times 3 is 27, right? And I keep doing this. What would be the next one? 36, and then 45, and I just keep going, right? And then over here, if I start looking at the multiples, I have 24 and then 36. Okay, so see, I found one that's a multiple of both. And I could use that as my common denominator. So I would now need to turn the 9 into a 36. And to turn 9 into 36, I have to multiply it by 4. So multiply by 4 over 4 here. And then here to turn 12 into 36, I have to multiply 3 over 3. And then I go straight across. So it's going to be ugly. 4 times 115. Anybody do that?
460.
4 what?
460.
60? 460? Over my 36 plus 47 times 3. 141 over 36. Did you have 36 on the bottom?
Yeah.
Yep, okay. And then add those together, what is that? 601 over 36? That's it, right there, right? That's the exact answer. Now, is it reduced? Is that actually the simplest form of the fraction? No? Can you go down further? So let's talk about how you would reduce this. Because when they're big numbers like this, sometimes it's hard to figure out, how to reduce it. So what I like to do is I like to come through here and just start going through different numbers and seeing if they divide into each of these. And the question is, what numbers do I try? Does anyone know what numbers I should try to divide into each of these? All your primes, all your prime numbers. Okay, so do y'all know what the prime numbers are? 1, 2, 3. They're the numbers that are only divisible by themselves in 1.
5 and 7.
5, 7. 8's not, right? 9's not. 11 is the next one. Then 13. And in fact, there's an infinite number of primes. You never run out of them. Have you all heard of primes before? Yes? Now, the reason why we do primes is this. Let's just say that 8 went into both of these. Let's just say, all right? Is 8 a prime?
No.
No, but if 8 goes into both of those, so does 2, right? Because 8 is an even number, so 2 should go in there also. If 6 goes into both of these, so would 3, Understand? So if you just look at the primes, you should be able to chip away at it. It's a little more efficient this way. So let's try, first of all, 1, you don't even worry about it because you'd be at the same place. 2, obviously it can't because this is an odd number that's even, so not going to be 2. How about 3? Does 3 go into both of those? You would have to try it, right? Maybe if you didn't know, you'd have to maybe get your calculator out or do it by hand. 3 does not go into 601, so it's not that. How about 5? No? 7? 7 does not go into 36. 11? No? So does this reduce? It doesn't? I would have to keep trying. And when would I stop with my primes? When I get to where? Anything bigger than 36, I would have to stop. Yeah, so this, I think this is all the way. I don't believe that goes any further. All right. That's it. Good question. Yes? Oh, you went back to a mixed number? That's fine. That's fine. I won't. If you leave it like this, you get full credit. If you go back to a mixed number, you get full credit. All right? What I don't want to see on the test is, let me use my, yeah, this is what I don't want to see. Hold on. Let me get my, I'm getting my calculator here. I don't want to see, I just don't want to see this. This is equal to 16.6944, like that, without any work shown or anything. All right? Because this is the correct answer if you convert that to a decimal. But this shows me that you did everything on your calculator and you don't know how to add 2 fractions together. And that's what we want to make sure you can do. Add 2 fractions. Get common denominators. Put them together. Understand? But if you get this answer and then after that you write this, that's okay. All right? All right. Other questions?
Can you go over number 6?
6 and
About this,
yes?
would it be possible to just add like big number, like with the full numbers?
Like 15.
Just add 15 and then just do 7 over 9 plus 11 over 12 and then just slap the mixed number.
That's a great question, and my answer is going to be yes with a little star next to it, okay? Meaning that I need to explain something. In this case, if you just say 12 and 3 is 15, and then 7/9 and 11/12, add those together and get that answer and slap that together, you would get the correct answer. My question to you would be, if I change this to minus, could you do it the same way? And the answer would be no. And so what I would encourage is only showing you things that are going to work all the time. So I would say avoid that. Just do the big numbers and be happy. Be as happy as you can, all right? All right? Okay, number 6, same section?
Yeah, the word problem.
The word problems. Sheila. Oh, Sheila likes to make cookies, I guess. I want to do number 5 first because I always have people that have trouble with 5. All right? It's just a weird problem. How many 3/4 cup servings are in 2/3 of a cup of yogurt? Yeah, let's talk about how we're going to get to that. But let's think about this. Which is bigger, 3/4 of a cup or 2/3 of a cup? 3/4, right? 3/4 is bigger than 2/3? So they're asking how many 3/4 servings are in 2/3 servings. And it's weird that way because they're asking how many times a bigger number goes into a smaller number. So that's why it's confusing when you read it. But I'm going to do this the same way that I told everyone to try and do these word problems if you're having trouble, and that's to replace the numbers with easier numbers. All right, so let's just switch it up. How many blank cups? You tell me. Make it a nice number. How many 4-cup servings? Let's change the problem. How many 4-cup servings are in What do you want? You want to go bigger? Let's go with something that would make more sense in our head. How many 4-cup servings are there in
20.
50? I'm looking for a number that'll go in easier. Right? Like how many 4-cup servings are there in 12 cups? 3. How are you doing that? Like what's the mechanical? You're doing this divided by this, right? Do you all understand that? How many 4-cup servings are there in 12 cups? You divide this number by this number. So if you just switch it up and you say how many 3/4 cup servings are there in 2/3, what you're going to do is take this and divide it by this, right? That's the operation. I hope that makes sense. Translating the problem into easier numbers can help you identify what the arithmetic is. Once you know what the arithmetic is, 2/3 divided by 3/4 is what we're going to do. And so we have to convert this to multiplication. Flip. And then straight across. So 8/9. That's how many 3/4 servings there are in 2/3 of a cup. There's 8/9 servings. It's weird. All right, now let's get to Sheila. Sheila was making cookies for the school parent-teacher dinner. In the blender, Sheila knew that she had put in 13 2/3 ounces of ingredients, right? After she was finished, she poured the mix into 2 1/4 ounce cup, little cupcake tins. 2 1/4 ounce cups. How many of these cupcakes would one batch of this mix make? So what's your thought here? Divide what by what? Divide this by this one. Now, again, we can translate this into easier numbers. If you had 36 ounces of mix, right? This is how much you're going to mix into the bowl. And then you're going to pour those into 2-ounce cups, right? 2-ounce cups. How many are you going to be able to make? 18. You're taking this and dividing it by that, right? That's what you're doing. So that's all I'm going to do. I'm going to take this and I'm going to divide this by this. So I'm going to write that down. 13 2/3 divided by 2 1/4. And I'm going to have to convert both of those over to improper fractions first. So 13 times 3 is 39, plus 2 is 41, over 3 divided by 9/4. And division becomes multiplication, flipping, right? Multiplying by the reciprocal. And then we go straight across. So what is that? 164 over 27. Now it says how many of these cupcakes would each one batch make? How much of the mix would be left over? So this is important. You know how you're pouring into the cupcake tins or whatever, and then you have a little bit left over. It's not quite enough to make a full cupcake. So what we need to do is figure out what this is as a decimal approximation. So on your calculator, 164 divided by 27 would give you what? 6 what?
I got 6 and 227, so I know the decimal.
Okay.
Decimal is 6.074.
074?
074.
Okay, and it keeps repeating. All right, so it's about, what this tells us is that we have 6 cupcakes, right? We have 6 cupcakes? Full cupcakes. We don't have enough to make a 7th cupcake. So the answer to the first part, how many of these cupcakes would one batch make, would be 6. It will make 6 cupcakes. Got it? Yes? How much of the mix is left over? Well, to do that, we need to take, what what was it? Yeah, 164 over 27, right? This is how many cupcakes we made? And see, there's different ways you could actually go about this. I could say, take away 6, and that'll give me a fraction of how much is left, right? So you would have to get a common denominator here and subtract, and that would be how much of a cupcake would be left over, but that's not what it's asking. What is it asking? How much mix is left over? So did anyone get that? How do you do it?
I multiplied the 6 and 27 and subtracted it from 164.
You multiplied the 6 and the what?
27, and then I subtracted it from 164.
I'm not following. You multiplied 6 times 27. Okay, yeah, you got a common denominator basically, because this is over 1. I'm not sure that's good. Look, I think the part that's confusing on this is you're going to make 6 cupcakes, right? This is how much is left over in terms of how much of a cupcake you have left. It wants to know how much mix you have left, not how much of a cupcake is left. Everyone's got this stunned look on their face, yes?
Okay, so you're going to use 41 over 3.
Okay.
And 9 over 4, and you're not going to divide it, but you're going to subtract. So you have to find the common denominator. So the 41 over 3 is going to be times by 4, and then 9 over 4 is going to be times by 3. So you have a common denominator of 12.
Okay.
You subtract those, so it's going to be 164 over. Wait, am I doing this?
Yeah, I think everybody is on the same page when it comes to the first part of the problem, right? You can get 6 cupcakes. This 0.074 is how much of a cupcake you have left over, and you need to know how much mix you have left over in terms of ounces. So let me try and rephrase it a different way that might help you. If this is how much mix we had, right? That's how much mix we started with. How much mix does it take to make 6 cupcakes?
164 over 27.
162.
No, this is what it. This is.
Okay, yeah, right.
How much does one cupcake take to make one cupcake? How much mix is that? 2 1/4. 2 cupcakes would be twice as much as this, right? 3 cupcakes would be 3 times, right? 4. So why don't I do this instead? Why don't I just see how much mix it took to make exactly 6? All right? I'm going to do 2 1/4 times 6. Wouldn't that be exactly how much mix I used to make 6 cupcakes? All right, so I have to convert this over. This is 9/4 times 6 over 1, which is what? 54 over 4. With me? This is how many ounces of mix it takes to make exactly 6 cupcakes. Right? That's how much mix it takes. Now, this is how much mix I started with, right? This is the mix I started with. Take that, subtract that, that's how much mix you have left over. I think that's the cleanest way to do that last part. But do you all follow it, what I'm doing?
Are you subtracting 4 over 4 minus 13 that you
I'm going to do this minus that one. Okay, so I'm about to do that right now. I just want to make sure people are following me here. I take my 13 2/3, which is really 41 thirds, right? That's this, converted. And I subtract from it 54 fourths. If I can do that, then that will tell me how much mix I have left over. Do y'all get this? The mix I started with, the mix that I used in order to make exactly 6 cupcakes, that difference should be how much mix I have left over. So we need a common denominator here. What would be the common denominator? 12. So I multiply 4 here, 4 here, 3 here, 3 here. So what do we have? 164 over 12 minus 162 over 12, which is 2/12, which is 1/6. So you subtract, keep the denominator, reduce the fraction. 1/6 of a cupcake left over. Now, I think that's good. Let's move on. Yes?
We do 7.
7.
Word problems.
Uh-huh. One day, Mr. Sanders walked 4.5 miles to one store and then 2 1/5 miles to another. Then he again walked 7.56 miles to a third store. How far did he end up walking altogether? So what are you going to do? Just add them all together, right? Add all those together. So 4.5 plus 2 1/5 plus 7 5/6. Common denominators, or not common denominators, improper fractions on all of these first. So this one will be what? 9 halves, 9 over 2, 11 fifths, and what is that? 47 over 6? There you go. Now you need a common denominator. 30? So you have to turn all of these into 30s. So I'm not going to go through and show the little multiplications. But this over 30, I have to multiply top and bottom by 15. So what would that give me? 135 over 30. Here I have to multiply the top and bottom by 6. 66 over 30. And then the last one, multiply by 5. To what? 35, yep. Over 30. And then now they all have the same denominator, so I just add straight across. And what is that? 436 over 30. To what? 218 over 15. And you could leave it like that. And you could also, if you wanted to know, you could turn it back into a mixed number, okay? Or you could do it as a decimal, or leave it like that. Okay, I think that we should probably move on to where we left off last time. Yes?
Quick question. Can you add those separately? Like, you do like 4 1/2 plus 2 15s and do that, and then whatever you get, you add that with 7.
Like add these two first and get an answer?
Like, okay.
Sure,
Okay.
yeah. And then add that after? Yeah, yep. All right, so last class we were doing order of operations, and I showed you that a lot of you had been taught or didn't quite remember the order of operations correctly, just to kind of make a point that we need to pay attention because there may be something here that we thought we knew that's not right. So I have a big mess of problems for us to do here, and I thought we might start out with the first one, all right? 5 minus 3 plus 72 times 10 minus 2. Keep in mind, all of this is still supposed to be kind of review. Like, you've all supposed to have known how to add fractions and subtract fractions, and order of operations is something you've seen. We're just trying to get our brains going again. So what am I going to do first here? 10 minus 2, because it's in parentheses, right? So I always want to start with anything that's in parentheses first. If there's something in there I can do, I do it. So I'm going to say this equals 5 minus 3 plus 72, and then this is going to turn into 8, right? So I put an 8 here, and my question to you is, what is the operation occurring between the 72 and the 8? It's multiplication. So you need to indicate that somehow. One way would be to put a dot. Another way would be to put a parenthesis around the 8, and that would imply that these two are multiplied. They mean the same thing. I prefer parentheses, so I'm going to put parentheses there. Now with order of operations, once you've done an operation, you have to start the whole process over again. So I go here and I say, do what's in parentheses first. 8. There's nothing to do, right? So I move on to the next thing. Exponents. Do you see any exponents? Exponents are powers, right? Nothing here? So I move on. What's next? Multiplication or division, whichever occurs first as I move from left to right, reading it like a book. Do you see multiplication or division? Yes, right here there's multiplication. That's it. So I'm going to do that next. 72 times 8? 5 what? 576. All right, start over. Parentheses, there are none. Exponents, there are none. Multiplication, division, nope. Addition and subtraction comes next, from left to right, whichever appears first. So I'm going to do this subtraction first. So 5 take away 3, 2. 2 plus 576, and we're pretty much there, right? Just add 578, we're done. We good? All right, I'm probably going to do most of these examples here. I might keep some for you, and then I'm going to have you work on your own and see if you can do some. I'm going to have you actually start your homework in class and count it as a quiz grade, all right? I'm not going to grade it. I want to see effort. I'm going to walk around, kind of see where everyone is. All right, let's look at number 2. 2 plus 2, parentheses, 3 minus 6, parentheses, minus another parentheses, 1 plus another parentheses, 1 minus 4, close parentheses squared, close parentheses squared. Yeah, that. That looks pretty ugly, right? All right, so we're going to do order of operations. We start out with parentheses. There are several parentheses in here, right? If you have a parentheses like this, where it's by itself, right, like this, then that qualifies as something you need to do first. But you also have this parentheses, right? And it starts here, we say it opens here, and it actually closes right here on the back side. But within that parentheses, there's another set of parentheses. So when you have clustered parentheses like that within each other, you always go inside to the one that's buried first, and you do that one first. So if I were going to be following correct procedure here, I'm actually going to do that first. All right? That's what I'm going to do. And just get into a habit of rewriting everything. Okay? Don't be afraid to write on paper. It's okay. Use up the paper. Not a big deal.
How do you know I do that first?
That's what I'm saying. Anytime you have parentheses inside of other parentheses, you do the inside one first. So what is 1 minus 4? Negative 3. So this is going to turn into a negative 3, right? I'm going to put negative 3 right here. Now this is where things get a little tricky. Because what are you supposed to do with this negative 3 after you determine what it is? You're supposed to square it, right? So I'm gonna finish this, but I want to ask you a question. Over here, separate thought. Is there a difference between this and this? Are these the same answer, or are these different answers? Different? Same? What is the answer to this one? 9. What's the answer to this one? 9. Okay. Any other opinions? When we put this squared right here, right? What we mean is to square whatever this is whatever we call the base. Only square the base of this exponent. So the base of this exponent is this 3 right here. The negative out here is actually a -1 being multiplied by the 3 that's being squared. So what I'm telling you is that this notation right here means this. So without parentheses, you would square the 3 first. 3 times 3 is 9. Times -1 is -9. That is the correct answer to this one. This one, however, says that you're going to do the whole thing squared, which means -3 times -3. See, the parentheses pulls that negative in there with it, and it's part of what's being squared. So anytime you have a negative times a negative, it becomes positive. So the answer to this one is +9. There is a huge difference between these two notations, is what I'm trying to get at. They're not the same. Yes?
So that goes to the calculator, so if
That is right. Yes. If you right now on your calculator type in -3 squared, you should get -9. If you put parentheses around the -3 and square it, you should get +9. Now, the reason why that's important is because right here where we found -3, and we are going to square it, which of these two is it? Top one or the bottom one? It's the bottom one. Because whatever was here, right? Whatever is in here is in parentheses is being squared. So this should be -3 squared. And then I have to close off this parentheses and put squared. So close it, squared. Y'all see that? Okay. Let's continue. Order of operations. Start over. Parentheses. Do you have parentheses? Yeah, you've got some here. You've got another set here, right? I can do this one now if I want, and I can also work on this one. These are kind of separate. They're not clustered. So why don't we take care of this one real quick? What's 2 plus 2? What does this become? -3. And I'm going to put that right here. And what's the operation that's occurring between this 2 and that right there? Multiplication. So I should probably put that in parentheses to imply the multiplication. Yeah, I know that camera kind of gets in your way, especially if you want to move the desk a little, back it off, you can. Okay. All right, that okay with everyone? All right, I'm going to put my minus sign here. I'm going to go ahead right now, and I'm going to work on the inside of this parenthesis also. So I'm working in here, and I see exponents, right? So I need to do this before I do any addition. So what is -3 squared? +9. So this becomes 1 plus 9, and then all of that will be squared in a minute. Next line. 2 plus 2 times -3 minus, let's go ahead and put these two together, 10, and that 10 is being squared. This 10 squared. Order of operations. I need to do this exponent, right? Before I do this multiplication, before I do any addition or subtraction. So 2 plus 2 times -3 minus what? 100. 10 squared is 100. See, notice this negative right here is not inside the parentheses, so you just ignore it and you do the 10 squared first. What would be the next thing I do? Multiply the 2 times the -3, which is -6. So I'm going to write 2, and should I write plus -6? What should I write? -6. Because when you add a negative, it's the same as subtraction. And then we can write down this part, -100. All we have left is subtraction, right? Left to right. What's 2? Take away 6. -4. Take away 100. -104. Okay. Order of operations. Let's look at 3. 3 is, I think, a little easier than that one was. Three is square root 5 squared minus 3 squared. So the square root is actually like a parentheses, all right? It's actually like a parentheses. So we're going to do anything inside of that square root first. So what is 5 squared? 25. And what is 3 squared? 9. And continuing, we do what's inside first. What's 25 minus 9? 16. And what is the square root of 16? 4. So when we say square root of 16, we're saying what number, when we square it, would give you 16? 4 squared would. Now, the reason why this is up here is because of this mistake that some students make. Anybody have any guess as to what some students do with this? They cancel out the square root, they cancel out the squareds, and they write 5 minus 3. It happens, okay? They say, oh yeah, I know a square root undoes a squared. That's true if it's multiplication between these two. But if it's addition or subtraction, you can't do that. So some people would come up with 2, and of course that's wrong, right? All right, next one. So I have this -8 and I have these 2 bars on the side. What are those called? Or what's that called? The absolute value. And the absolute value of a number is just whatever that number is, but the positive of it. So if this is -8, the absolute value of -8 is +8. Right? We can treat an absolute value bar like a parentheses. So we look in here. There's nothing to do inside, right? There's nothing to do. So I just take the absolute value of -8 and get 8. But I also have a parenthesis over here, which I need to do. So I think I'll do these at the same time. This is going to give me 8 minus 9 times, this gives me what? -1. So it's -1, and I need to put this in parentheses, don't I? Because it's implied multiplication. If you don't put the parentheses, you might think that that's 9 take away 1. Right? 9 minus 1 instead of 9 times -1. What should I do next? This right here, multiplication. 8. Now I heard someone say it's -9 times -1. That's okay. I want to make sure that everyone knows if you multiply a negative times a negative, of course you get what? Positive. So this should be 9. But what do I have to have between these?
A negative.
Well, it was negative times negative, which is positive, right?
Yeah.
So this should be a plus sign here. So we should get 17. All right. Getting into some fraction stuff now. How about 7 to the 3rd power plus 2 times 4 over 17 minus 3. So for this problem, this division bar right here separates your top and bottom, what we call the numerator and denominator. You must completely figure out what's up here first. Take this all the way down, as simple as it can go. Then simplify everything down here, and after you're done doing that, then you can put them together. At no point in time before that can you put these together. So I'm going to start out on top. I see exponents, I see parentheses, but the parentheses, there's a 4 inside. I can't do anything to that, right? So I'm going to do the exponent first. 7 cubed. 7 times 7 times 7, which is 343. 343 plus 2 times 4 over, I guess I can do the bottom now also, right? What is this, 14? So I'm doing the top and bottom separately. I could have multiplied this together also at that same time, but I'm kind of going in baby steps here. 343, what? Plus 8, because you're multiplying 2 times 4 over 14. And this gives you 351 over 14. And maybe that reduces. I don't think so. It does not. Y'all look bored. How could you possibly be bored in a math class? I don't get it. So you want a little 5-minute off topic, or you just want to keep grinding? I can keep grinding. Keep grinding? Okay. All right. The next one. I've put this one on a test before. I've put one like this on a test before. All right, so I see 1 plus, right? So addition is one of the last things I ever do, so I'm not going to worry about that right now. I see a big division, so I'm going to work with the top and bottom, figure out what those are, and then I'll put them together. So let me start with that top piece. For the top piece, I think I'll do that kind of like scratch work over here on the side. I'm just going to figure out what these two fractions added together are, which means I have to get a common denominator and put them together, right? So my common denominator here would be 15. So you would get 6 over 15 plus 5 over 15. I'm assuming you know to come in with 5 over 5 and 3 over 3 and put those together. And that should give you 11/15. So if this step from here to here takes you a little more time, that's okay as long as you know how to do it, right? As long as you know what you're introducing. That's 11/15. And then what about the bottom? 2 cubed. 2 times 2 times 2, 8. 8. So we have, I can rewrite this as 1 plus 11/15 over 8, like that. Any questions? No? What's up? I see like people squinting. Huh? Oh, because, all right. I saw you squinting. Okay. I forgot to put the 1 in front of the 5. All right. Thank you. 11/15 over 8. Now, the reason why this problem is given is because of this situation right here and whether or not we understand what's going on. Right here. Like, how do we do this? So let me write something down. I want you to tell me what this is.
divided by 4.
12 divided, so 4 divided by 4? Okay, maybe. Might be. So the way you looked at it is you said, okay, let me do 12 divided by 3 first, which is 4. And then I'm going to do 4 divided by, right? If that's 4, 4 divided by 4, that should be 1, right? But someone else might have said, no, I want to do 3 divided by 4 first, right? Which is 0.75. Take 12 and divide it by 0.75, and it's not 1. Yeah? You get 2 different answers depending on which way you look at it. So this right here is considered bad notation. This is my fault for not writing this properly. I need to make one of these bars bigger in order for you to be able to determine which one to do first. So with the bar being big like this here, that means you do this one first, which would be 4, and then you divide that by 4. If I had written it this way, you would do 3 divided by 4 first, and then divide that into 12. Do you see the difference between the two? So when we're over here and we did this, we got this fraction up here, that's 11/15. And then this bar right here is going to be the big bar, and then below it we have 8. Got it? I'm going to rewrite 8 as 8 over 1. And now you can see that this is a fraction divided by a fraction, right? What I'm trying to point out is that if I didn't turn that to a fraction and you just wrote that this way, maybe you would have done that. You could argue that one way you could do it is 11 over 15 divided by 8. Another person could say it's 11 divided by 15 over 8. Two different ways of interpreting it. And that is not right. This bar right here is always the big one. Understand? All right, so 8 over 1. So let me do that over here on the side. 11 over 15 divided by 8 over 1. And to do division, I have to flip. So 11 over 15 times 1 over 8, which is 11 over 120. Okay. So I come back over here. 1 plus 11 over 120. What's next? Yeah, you have to put these two together, which means you're adding two numbers, two fractions. You have to have a common denominator. So I need to rewrite that as 1 over 1, that's what 1 is, plus 11 over 120. And I'm just doing that to write it as a fraction. And then I need a common denominator, so I multiply top and bottom here by 120. I get 120 over 120 plus 11 over 120. And that will give me my final result, which is 131 over 120. Question?
Just done what you usually do, like 1 multiplied by like. Yeah.
Oh, like 1 times this plus 11 over 120?
Yeah.
You can't, that won't work.
Oh, okay.
No, I mean, okay, it works because this is a 1, all right? It works because it's a 1. But that's the same as, look, if I write 1 and 11 120ths, mixed number, this is this. That's what this means. So it works that if you did that, you should come up to this. But that would only work if that's a 1. Chances are it's not going to be a 1. It just happened to be a 1 here. All right. I can't help myself. Sorry, I cannot help myself. All right. These were the prime numbers, right? Sorry, I know you wanted me to stay on track. But if you want to become an overnight billionaire, there's a math problem that needs to be solved. And if someone solves it, one of these days someone will, okay? You're either going to become very rich or you're going to become very dead, depending on how people will handle it, all right? So here's the issue. We send all of our information over the internet, right? We communicate. Some of the information we send, like through Snapchat and that type of stuff, not really heavily encrypted. Do you all know what it might mean when I say encrypted? I mean, all these things are flying around the air, right? Like when you send something through your phone, all these electronic digital signals are going through the air. You can't see them, right? If you could see them, like if you put on goggles and see all the information going on in this room, you would be blinded by it. It would be everywhere, right? If somebody intercepts that and reads it, okay, if it's encrypted, it becomes harder to read. So it's like scrambling up a message so that someone can't see what it says, right? You'll have a basic idea of that encryption? All right. The most powerful encryption that there is called Rsa encryption. And it is very simple, but very hard to defeat. And here's the idea, all right? I'm going to make it as basic as possible for you. I mean, that only because, not because I'm trying to, I just don't want you to think I'm saying basic because this is a 13, 14 class. I'm just trying to make it easy for everyone to understand, all right? Let me ask you something. If I tell you the number 15, can you tell me the two prime numbers that create that number? When you multiply, yes. This comes from the numbers 3 times 5, all right? The way RSA encryption works is that, and this is very loosely speaking, they take a number like this and they use that number somehow to scramble the message. Now I'm not going to get into details of how they do it, but they use this number to scramble it. To unscramble the message, you have to know these two numbers. All right? So it's like, let's say I want to send you a message right now. You tell me 15, okay? And everyone in the room hears you say 15, right? So I have my message and I scramble it using the number 15. And then I send it to you. Everyone in this room can hear that message being sent to you. But the only way to unscramble it is if they know that 15 comes from 3 and 5. Does that make sense? But everyone in here knows that 15 comes from 3 and 5, right? So the way RSA encryption works is that they take a number right here that's 80 digits long. All right? 80 digits long. So imagine an 80-digit number, whatever it is, 80 digits. And it's sitting there, and everybody in the room sees it. And I scramble my message with this 80-digit number. Then in order to unscramble it, you must know the two 40-digit numbers it came from. And believe it or not, that is very difficult to do. If somebody gives you an 80-digit number, it's very hard to come up with the two prime numbers that it came from. So hard, in fact, that the people who created RSA encryption said, look, we're going to use 80 digits for this reason. If every computer on the planet was trying to crack this code, trying to come up with the two 40-digit numbers, every computer on the planet, it should take 10 times the age of the universe for them to crack it. That's the standard for RSA encryption. So what happens? Computers get faster, things evolve, right? Sure, I'll just go to a 100-digit number. Use two 50-digit numbers. That makes it even harder for the computers to do it. What happens after that? I just go to I'll go to a 500-digit number, right? You're never going to run out of primes. You will never run out of primes. There are an infinite number of primes. And so you just picked, we have lists of primes, okay? And you just pick two huge primes. Okay, so if you wanted to create your number, you just pick two huge primes, multiply them together, that's easy. That would be what we call the public key that everyone sees. They scramble their message using it. Only you know where those two primes came from. And if you tried to ask, if someone around tried to break it with their computer, it's going to require everyone on the planet trying to do it at the same time. It's going to take 10 times the age of the universe. It's not going to happen. That's where we are in terms of encryption right now. It's basically impossible. That's why you hear about these things that, you know, everything going on in the world. You know, terrorist organizations, they can communicate, we can't break it. You know, and you in the back of their mind, you want to think, well, you know what, no, you know, we can. They're just not telling us, right? The CIA, you know, FBI, they can break, they can't break it. Okay, so RSA encryption, we all know this can't be broken. In fact, the program that creates it, it's not that complicated. But if you try and take that program like on a little jump drive out of the country, it's considered transportation of a munition. It's like the same as trying to carry a grenade or something out of the country. Yeah, it's crazy. Anyway, so if somebody ever is able to come up with a way to break a composite number down into its primes efficiently, quickly, with a simple algorithm, you will basically bring down to its knees all privacy, all encryption that we use in this world right now. And then what would happen is chaos, probably. So you'd probably either be swept under the rug or something, you know, or you would become very rich because you would have complete control over everything, right? you would have to go in hiding. So anyway, this is one of those, I just want to talk about it because look, math is, here we are, order of operations and stuff, but I mean, mathematics plays a real pivotal role in our lives every single day. And it's always been a back and forth between the people who are trying to protect the message, the encryptors, and then the code breakers, the people who are trying to break it. And it's been for a long time back and forth. Okay, these guys get the advantage, then the other ones figure out a way to break it, and then they have to go back and forth. But for a long time, this has been unbreakable. And nobody sees it going anywhere, like being able to ever defeat it.
So people who break it, do they just get lucky?
It's very difficult. I mean, this is a very difficult problem to do. I have a program on my computer right now. I could bring it up and I could type in a number and I could ask it if it, to come up with I could ask it. But if I give it a 40 or 80 digit number, we'll be here all day. Yeah. We will be here all universe, it's not going to happen, okay? It's not going to happen. All right. Sorry about that. Y'all ready to do one on your own? I think it's time for you to do something. Why don't you pick, I'll do one more of these. I've done up through 6. You pick one more, and I'll do one. We'll take a vote. Anyone see one there that just looks exceptionally bad? 11? 11 or 12. All right, let me do 11. So those big, long, stringed out ones with all the parentheses, those seem like the most intimidating? 15 looks awful? Okay. Well, we might have enough time for that. I want to spend like the last 15 minutes of you working, so. Rsa Encryption. RSA stands for the last names of the 3 guys who came up with it. I don't know their names, but.
Are they dead already?
I think they're alive still. Yeah, this happened back, I think, in the 40s or 50s is when they come up with it. 1940s, 50s. Oh yeah. Yeah. There's a book called the Codebook, if you're interested in that sort of thing. That's basically where I got all the information I'm telling you right now. And it starts out from like way back with like smoke signals, and it goes all the way to where we are now. It's a pretty cool book. All right, where do you start? My gosh, there's parentheses everywhere. So I've got parentheses here, and then inside that is this, but I can't do anything with that, right? Over here, parentheses, and then inside that, this parentheses. I can't do anything. -2 is -2. So you can start working in here and put those together, and then over here you can start putting these together. How about I do these first? Can I put those 2 together? What's 4 plus -6? -2. -2. So this equals 3 plus 2, and then this is -2. What should I put? Parentheses. Now the reason is because that's multiplication, so that's going to be multiplication. Plus, now inside this parentheses, let's do this. 1 plus, what's -2 squared? +4. What should I do next? How about this parentheses here? 1 plus 4? 5. So I'm going to put plus, and then this will be 5. I don't need parentheses around that 5. It's not wrong to put them, but I don't need them because this is addition, not multiplication, so it's okay to just put 5. What would be next? 2 times -2 would be here next, so 3 minus 4. You could put plus -4, right? I could put plus -4, but this is bad notation unless you put parentheses here. So it's better to just write -4 and then plus 5. And then from left to right, 3 minus 4, -1 plus 5. and then 4. And I said I'd look at 15. 1